In this lesson, we will discuss how to calculate the major losses in a circular pipe system. When using the control volume approach to analyze pipe systems, we often will use the conservation of energy equation for a control volume with one inlet and one outlet. Let's take a closer look at the head loss term HL. For convenience, the head loss is broken into two parts: the major losses, denoted by HL major, and the minor losses, denoted by HL minor. The major losses are related to viscous effects in straight pipes only. The minor losses are related to viscous effects in pipe components, such as valves, nozzles, bends, and so on. This lesson will only focus on the major losses. The minor losses will be discussed in a separate video. Before we begin, it should be noted that the subscript major does not mean that the major losses are always greater than the minor losses. There are many pipe systems in which HL minor will be greater than HL major. In a previous video, we derived an expression for the head loss in a straight pipe of length L and diameter D, which we're now calling the major losses. This expression is called the Darcy-Weisbach equation and states that the major losses are equal to the friction factor F times L over D times V average squared over 2G. Although we found the friction factor F is equal to 8 times the shear stress at the pipe wall, tau W, over rho V squared, we will soon develop a more convenient expression for F. These equations for the major losses and the friction factor are valid for both fully developed laminar and fully developed turbulent flows. First, we will examine fully developed laminar flows. The laminar shear stress in a circular pipe is negative viscosity mu times the velocity gradient in the radial direction dvx dr. The velocity profile for a fully developed laminar flow is the centerline speed vc times the quantity 1 minus the radial distance lowercase r squared over the pipe radius capital R squared. The average flow speed is 1/2 the centerline speed. Substitute these expressions into the equation for the laminar shear stress and remove 2V average from the derivative because they are constant. After taking the derivative, we are left with mu times 2V average over capital R squared times 2 lowercase r. At the wall, the radial distance is the pipe radius, capital R, which is equal to 1/2 the diameter. Additionally, the shear stress is equal to the wall shear stress, tau W. Plugging in d over 2 for the pipe radius, we find that the wall shear stress is equal to 8 times the viscosity mu times V average over d. Now recall the equation for the friction factor and plug in our new expression for tau W. After canceling terms, we are left with 64 times mu over rho V average d. Mu over rho V average d is equal to 1 over the Reynolds number. So the friction factor for fully developed laminar flows is 64 over the Reynolds number. Experiments show that this equation works well for flows with a Reynolds number below around 2000. For flows with a Reynolds number in the range of approximately 2000 to 4000, there is no accurate method of predicting the friction factor. For fully developed turbulent flows, the expression for the friction factor is different from the laminar expression because we must account for losses due to eddies. Unfortunately, we cannot derive an expression for the friction factor from theory, so researchers have conducted many experiments and have obtained empirical formulas for F. They found the friction factor is a function of two-dimensionless variables, the Reynolds number and the relative roughness, which is denoted by the absolute roughness epsilon over pipe diameter d. The absolute roughness of a pipe is the distance that imperfections at the pipe wall protrude into the flow. Typical values for the absolute roughness of new pipes of different materials is available in many sources, including fluid mechanics textbooks. Here we have a fully developed turbulent flow. The viscous wall layer thickness delta W is exaggerated for clarity. If we zoom into the wall, we would notice that the wall is not perfectly smooth, but rather consists of small imperfections that have an average height of epsilon. The absolute roughness is usually quite small for new pipes and related to the pipe material. Very rough pipes, such as those made of concrete, have absolute roughness values that are typically tenths or hundredths of an inch in size. Some materials, such as glass and plastic, have negligible values for the absolute roughness, and pipes made of these materials are said to be hydraulically smooth. The roughness disturbs the flow inside the viscous wall layer, and these disturbances can propagate outside the wall layer to the rest of the flow. In turbulent flows, any disturbance outside the viscous wall layer will tend to produce eddies. If the absolute roughness is similar in size to the viscous wall layer thickness, the wall will enhance eddy formation and increase major losses. Hydraulically smooth walls disturb the flow much less, thereby reducing eddy formation and lowering major losses. For laminar flows, any disturbance outside the viscous wall layer will tend to be tamped down, preventing eddies from forming. As a result, the roughness does not impact major losses for laminar flows. Using experimental data, an empirical formula for calculating the friction factor for turbulent flows has been developed. This formula is called the Colebrook equation, and it relates three dimensionless quantities: the Darcy friction factor F, the relative roughness epsilon over d, and the Reynolds number. This equation works well for flows with a Reynolds number greater than 4,000. Notice that it is not possible to solve the Colebrook equation explicitly for F. However, computers can find F quite easily using a root-finding algorithm if the relative roughness and Reynolds number are known. Alternatively, if you don't have access to a computer, you can use an iterative scheme to find F through a hand calculation. First, you guess a value of F, then check if the left side of the equation equals the right side of the equation. If the two sides of the equation are almost equal, you are done. If the two sides of the equation are very different, though, adjust the value of F and try again. Historically, it was very time-consuming for engineers to calculate F using the Colebrook equation, since calculators and computers were not readily available, and it may require many iterations to determine F. So a graphical representation of the Colebrook equation, called the Moody chart, was developed, which allows engineers to estimate the friction factor in seconds. The Moody chart will be discussed in a future video. Researchers have also developed formulas that allow you to calculate F directly. One such formula is the Halland equation, which differs from the Colebrook equation by less than 2%. It has the advantage of allowing you to calculate the friction factor directly if you know the relative roughness and Reynolds number without needing to perform a time-consuming iterative process. In summary, the Darcy-Weisbach equation is used to calculate the major losses for both fully developed laminar and fully developed turbulent flows. For fully developed laminar flows, the friction factor is only a function of the Reynolds number and is equal to 64 over the Reynolds number. For transitional flows, there is no accurate method for determining the friction factor, and for fully developed turbulent flows, the friction factor is a function of both the Reynolds number and the relative roughness. It is determined through calculation using the Colebrook or Halland equations, or using the Moody chart, which is a graphical method.